We will continue with the lecture on static friction. What we had in the previous video was a block M. This block was resting on a solid floor. There was a gravitational force acting on it. There was a normal reaction in response to that. There was an effort E being applied by a person on this block, and there was a friction force which was resisting it. And having a condition that this block is in static equilibrium gave us two equations. First, that the normal reaction is equal to mg, and that the friction force is equal to the effort being applied. And we had left off by saying that this equation number 2 is valid as long as f is sufficiently small. Now, to understand what f is sufficiently small is, we can create a thought experiment. What we'll do over here is we'll have a graph with time as one axis and force as another axis, and the person who's pushing this block will increase the force with which he or she is pushing the block, let's say linearly. So linearly with time, the effort E is being increased, and we will measure the friction force that is being generated, and we'll plot it on the same graph. Now what we will notice is that initially, while we are close to the origin, the friction force F, which is the line which is in green, rises along with this curve. That is, these curves are coincident. After crossing a certain critical value, this friction curve will diverge from this curve. So once it hits this value, it could either stay constant, it could either increase but slower than E, or it could actually decrease. So these are all possibilities of friction. Now what this effectively creates is a gap, and this gap means that this equation is not being satisfied. And when this equation is not being satisfied, this body is no longer in static equilibrium, which means this body starts moving. So as soon as we have crossed this point, this body starts moving, and this is familiar whenever you're pushing a heavy object. You have to push till a certain force, and beyond that the body moves. So this body will stay in equilibrium as long as we are within this region, or as long as F is less than F critical. So we can describe this mathematically as, if F is less than F critical, we have static equilibrium, and if F is equal to F critical, we have something called critical equilibrium. And finally, if F is greater than F critical, body moves. Now, finally, what we have seen till now is we put in all the forces that are acting on the body. We put in a friction force to compensate for it. When we use the conditions for static equilibrium, we get the value of friction. And once we have gotten the value of friction, all we have to see is whether this value of friction is less than F critical. But how can we test that if we do not know what F critical is? So this is where the coefficient of friction comes in, and this is a simple model for friction. Friction is actually a very complicated phenomenon involving surface textures and atomic forces, but if we do not want to get into that complexity, we can have a simple model which says that F critical is equal to mu s into n, where n is this normal reaction and mu s is a coefficient. And this mu s is basically captures the quality of the two surfaces which are interacting. So if the two surfaces are smooth, this value of mu s is less. If the two surfaces are rough, this value of mu s is more. So this is how we find the value of F critical. This is the coefficient of static friction. And finally, if we try to write a flow chart for how to solve friction problems, this is how it would go. 1, create an FBD to add other forces. 3. Add friction at contact surfaces. 4. Balance forces to get friction force, and finally check that F is less than F critical. So in the next video we'll solve a simple question on friction, and we will then use this concept in further videos.